So chapter 3 will now be getting into probability. So 3.1 is going to be concepts of probability. So for a couple definitions here, a probability experiment is just going to be an experiment where measurements or specific counts are obtained. The results in an experiment are going to be the outcomes, and the important one here is sample space. A sample space for a probability experiment is going to be the set of all possible outcomes. So we'll be using that term a lot. Okay, so for the next thing, for tree diagram, a tree diagram is going to help us determine the possible outcomes of a probability experiment, which is the sample space. So let's do an example just so we can see how it is drawn out. So let's say an experiment consists of tossing a coin and then rolling a six-sided die. Let's identify the sample space using a tree diagram. So as soon as you see the word sample space, we should be thinking set of all possible outcomes. So we want to know the set of all possible outcomes from tossing a coin and then rolling a six-sided die. So let's do a tree diagram. So it's going to be the first thing, we line them up like this. The first thing is tossing a coin. Then you put the options below for tossing a coin. When you toss a coin, we can either get heads or we can get tails. So the next thing is rolling a die. Put roll the die. So now you have to go to each possibility from the first one, which is tossing a coin, and give it every possibility for the second one, which is rolling a die. So to do that, you have to give it branches, hence why it's called the tree diagram. So we can either roll a 1, we can roll a 2, we can roll a 3, we can roll a 4, 5, or roll a 6. So that means 6 of our options here are we toss the coin, we get a heads. Then we get a heads and a 1, a heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. And now we do the same thing for tails. So if we toss a tails, then either we're going to roll a 1, roll a 2, roll a 3, roll a 4, roll a 5, or roll a 6. So to determine the sample space, put sample space. So since this is a set of outcomes, I'm going to write this with squiggly brackets or braces. So the total possible outcomes here, we either get a heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, or heads and a 6. And then for tails, it's either going to be tails and a 1, tails 2, tails 3, tails 4, tails 5, and tails 6. So from this experiment, this is the total possible outcomes. So we can see here that there are 12 possible outcomes if we counted all of them up. So we only had 12 possible outcomes here, so it was pretty easy to actually list them all out. So usually we will not always be able to list out all of the outcomes in an experiment, but we still might want to know how many outcomes are possible. So if we can't list them out, something that we can do to figure out how many outcomes there are is the fundamental counting principle. So this is one of the most important little theorems or principles in probability. So the fundamental counting principle is going to find the number of ways 2 or more events can occur in a sequence. So what it says is that if one event can occur m ways, so m and n are just going to represent number of ways. If event 1 can occur m ways, and then another event can occur n ways, then the number of ways that 2 events can occur in a sequence is going to be the product m times n. So you multiply. So there can be more than 2 events. There can be 3, 4, but either way, you just multiply the number of ways that they can occur individually, and that'll give you the total number of ways they can occur in a sequence. Okay, so let's identify, I'll do some examples. Let's identify the number of possible outcomes using the fundamental counting principle. So let's go back to that example. We flip a coin and then we roll a 6-sided die. So for flipping a coin, we know that there are 2 outcomes, right? There's heads and tails. For rolling a die, rolling a 6-sided die, there are 6 outcomes. So thanks to the fundamental counting principle, the total number of outcomes we multiply is going to be 2 times 6. So 2 times 6, which is 12 outcomes, which we already knew because we listed them out on the previous page with the tree diagram. Okay, so let's make it a little more difficult here. So let's say you're purchasing a car and you have 3 choices. You have 3 things to choose from: the make, the car size, and the color. So for the make, let's see, you can choose from Mazda, Ford, or Chevy. The car size is compact or midsize, and the colors are blue, black, silver, and red. So we want to know, based on all of those possibilities, how many different ways can we choose a car. So let's kind of break this down. So the make, there are 3 different outcomes or choices, or however you want to say it. I'm going to use outcomes. There's 3 different outcomes for a make. It was Mazda, Ford, Chevy, so that's 3. For car size, there are 2 options, which means 2 outcomes. We had compact or midsize. For color, we had 4 outcomes. We had black, blue, silver, and red. So the total number of ways that we can choose a car, which I'm just going to once again write it as outcomes, is going to be all of those being multiplied together. Fundamental counting principle. 3 times 2 times 4, so there's 24 total outcomes. There's 24 different combinations for choosing a car given those 3 options. Okay, so what I'm actually going to do, I'm going to create a tree diagram. So I'll start the setup for it, and then I'll kind of pause the video and then fill it in, so you don't have to wait while I'm filling it in. So for the tree diagram, we have make, and we have the car size. So it doesn't matter which one you put first. We could have put car size first. We could have put color first. It doesn't matter. And then we have color. So starting off with the make, we can have Mazda, and then we said we could have Ford, or we can have Chevy. For car size, what I'm going to do for car size, it said compact and midsize. I'm going to give each one of these makes one of those car sizes. So we can either have compact and midsize. So I'm just going to fill in the other ones real quick also. So now Ford and Chevy both have compact and midsize branches coming off of them. So now for color, I'm going to go to each one of those car sizes and give each one its own, all of the colors that were options. So for compact, we can either have, we could have black, we could have blue, we could have that silver and red, I believe. And now I'll pause the video again. I'm gonna go and give each one of the rest of them those colors. So now all of those car sizes got their own individual colors for all the color options. So it looks something like this. So obviously pretty big. I'll try zooming out a little bit. There we go. So all we have to do if we wanted to count the total number of possible outcomes, you have to go to the rightmost column and you have to count how many options are there. So that would be the color column. So you count them. So 1, 2, 3, 4. 1, 2, 3, 4. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 24. So there are 24 possible outcomes if you counted them all. Which, when we did the fundamental counting principle, that's exactly what we got. So you could have, if you were counting off the total number of outcomes, you could say you can get a Chevy midsize black, Chevy midsize blue, Chevy midsize silver, Chevy midsize red, Chevy compact black, Chevy compact blue, and so on. Not going to read them all off. Okay, so let's do a couple more examples using this principle. So let's say we have a password for a security system that consists of 4 digits, and we want to know how many passwords are possible given these certain restrictions. So what I like to do for these questions is we have 4 digits. So I like to write it like this. We have a digit, 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 and digit. We have 4 of them. So it probably seems kind of silly, but it might help you guys. So before we even get into the problem, I just want to make a quick note. There are 10 digits, and the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 10 of them. And before we get to the next problem, because we'll need it, there are 26 letters in the alphabet. Okay, so let's get back to this problem here. So how many passwords are possible when each digit is only used once? So that means we cannot repeat digits. So cannot repeat. So what that means, for the first digit, we have 10 options, right? So we just go in order. First one, we have 10 options, 10 digits. We cannot repeat that digit. So for the second one, we only have 9 options. We cannot repeat either of those 2 digits for the next one, so we only have 8 options. And lastly, for the fourth digit, we can't repeat it. We can't repeat the 3 first ones, so we only have 7 left. So it's 10 times 9 times 8 times 7. We're multiplying them because of the fundamental counting principle. There are 5,040 different combinations, which is a decent amount for only 4 digits allowed for a 4-digit password. So next one, let's say that the digit can be repeated. So that means for the first one, we have 10 options. Second one, we can repeat it, so we have all 10 options. Same thing for the third, same thing for the fourth. We have 10 options for all 4 of the digits. So 10 times 10 times 10 times 10 is 10,000. So that actually, just being able to repeat it, that almost doubles the possibilities for how many passwords we could have. Okay, and then for the next one, each digit can be repeated, but the first digit cannot be a 0 or a 1. So if the first digit cannot be a 0 or a 1, that's eliminating 2 possible options. That means there's only 8 options for the first one. And now after this, we can repeat the digits. So that means times 10, we can repeat it. Times 10 for the third, and 10 times 10 for the fourth. Multiply all those together, we get 8,000 possibilities. Okay, so that one, maybe you didn't need to write that D out like I had at the top of the page. The next one you might want to, just so you can take a look back up to it. So we want to know, it's a license plate one. So we want to know how many license plates are possible when it consists of 3 letters and 4 digits, and then we have these 2 questions for it. So I'm going to write this out. So we have 3 letters. So we have L for letter, 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 and then we have 4 digits. So digit, 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 and digit. So first question, we want to know how many are possible if the digits and the letters can be repeated. Okay, so for the first option, it's letter. There are 26 letters. So 26 for the first one. The second one's also a letter. We can repeat it, so there's all 26 options left. Same thing for the third one. So for digits, the digits can also be repeated. So that's going to be 10 times 10 times 10 times 10. So 10 digits, they all can be repeated, so they all have 10 options. We multiply all those together, so that's 175,760,000. So that's a large amount of options. Okay, and then for B, the digits can be repeated, but the letters cannot be repeated. So the letters cannot be repeated. So for the first one, we have letter, letter, letter. So we have 26 options for the first one, but the letters cannot be repeated. So that means we only have 25 for the second one and 24 for the third one. Okay, and then for the next thing, for digits, the digits can be repeated. So that means there's 10 options for all 4 of them. So we multiply all those together and we get 156 million. So just by not allowing the letters to be repeated, we just chopped off about 20 million potential options. Okay, so that's the fundamental counting principle. Super, super, super important. So for the next thing here, we have types of probabilities. So there are 2 different kind of types of probabilities, different methods that we use to calculate probabilities. The first one is classical probability. So when it's also called theoretical probability. When each outcome in a sample space is equally likely to occur, this is the one that we'll be using. So this is read, this P with parentheses and then E. This is read as the probability of event E. So the probability of event E happening is the number of ways event E can occur divided by the total number of outcomes in the sample space. So let's do some examples here. That probably sounds more confusing than it is. So for example, let's say that you roll a 6-sided die. We want to find the probability of each of the following events. So before I even do that, let me just mention real quick, when we're getting an answer here, so find the probability, our answer can be as a fraction, it could be as a decimal, or we can convert it to a percent. All of those are acceptable answers, acceptable ways of showing our answer. Okay, so we roll a 6-sided die. We want the probability of event A, which is rolling a 3. So we want, what's the probability of rolling a 3? So I'm sure most of us know that the probability of rolling a 3, there's 1 3 on a 6-sided die. So the probability would be 1 out of 6. The way that I could set this up if you were struggling with a question like this, event A is rolling a 3. The only way we can roll a 3 is if we roll a 3. So I'm just going to put 3 in the braces to represent that's the only way we can do it. For S represents sample space. And then remember, sample space represents the total number of possible outcomes. 6-sided die, that means the total possible outcomes are rolling a 1, 2, 3, 4, 5, or a 6. So based on kind of bringing back that definition up here, it's the number of ways event E, which in this case we're calling event A can occur divided by the total number of outcomes in the sample space. So we can only do this, there's only one thing in event A, and that's rolling a 3. There's 6 in the sample space, so it's 1 out of 6, which once again we probably already knew. So that's an acceptable, oops, I forgot the probability of event A. Probability of event A happening is 1 out of 6. So that's an acceptable answer. or as a decimal, that would be 0.167. As a percent, that would be 16.7%. So all acceptable answers, 1/6, 0.167, or 16.7%. So for the next one, for rolling a 7, so we want the probability of event B happening, which is rolling a 7. So event B, there are actually no 7s on the 6-sided die. The way you denote that for a set is the empty set, which is just the braces with nothing in it. And for the sample space, once again, that's 1, 2, 3, 4, 5, 6, 7. Or 5, 6, sorry, 5, 6. So it's the number of ways that event B can occur, which is 0, divided by the total number of outcomes possible, which is 6. So 0 out of 6, so just 0. Or 0%. Because there's no 7, obviously no 7 on the 6-sided die. Okay, let's make it a little bit more difficult here. Event C, rolling a number less than 5. So we want the probability of event C happening. So let's see what events or what outcomes satisfy event C. So a number less than 5 are 1, 2, 3, and 4. The sample space, once again, 1, 2, 3, 4, 5, and 6. So the probability of event C happening, there's 4 different outcomes in event C. 6 total outcomes in the sample space, so 4 out of 6. That simplifies to 2/3, which would be 0.667, 0.66 repeating, but 0.667 we'll round to, which is going to be 66.7%. So once again, all acceptable answers, doesn't matter which one you use. So there's a 66.7% chance that you roll a number less than 5. Okay, and then the next, so that was classical or theoretical probability. The next type of probability is empirical probability. So empirical probability is based on an observation that from an experiment that we've already done. So the empirical probability of event E happening, it's just the relative frequency. So the probability of event E is the frequency of event E divided by the total frequency, which with symbols, it's going to be F over N. So it's kind of the same concept, except we already have data and we're basing it off of the data from an experiment. So that numerator is essentially how many times E happened, how many times the event happened, divided by the total outcomes. So once again, just setting up a little fraction here. So looking at this example here, so suppose we conducted a survey of people who recycled, and the results are right here in this table. So the 5 possible outcomes, or the 5 possible responses that people in the survey could respond with were always, often, sometimes, rarely, or never. And then on the right, is the frequency. It's how many people made those responses. So we want the probability that a randomly chosen person will say always. So this is going to be the probability of event E. I'm just going to call this event E. It's going to equal the number of times it happened divided by the total number of outcomes. So frequency over total number of outcomes. So for always, that's right here. 1,054 people said always. The total number of outcomes is going to be the summation of those frequencies. So remember, the sigma represents summation, which is adding. So I'm just adding that right column up. If we add all those numbers, that would give us 2,451. So that's our denominator. So all we have to do is divide it. And that would be 0.43. which would be 43%. So 43% of the people essentially responded with always. Okay, so the next thing that we're doing here, this law of large numbers, this is arguably one of the most important concepts in probability. So the law of large numbers, the other name that's used for it would be like the law of averages, that just you would say day to day, but it's technically called the law of large numbers. So this states that as an experiment is repeated over and over and over and over again, the empirical probability of an event is going to get closer to the actual or the classical probability of the event. So the empirical probability, what the data tells us of an event, is going to approach the classical probability of what should actually be happening. So for example, let's say we toss a coin over and over again, and then we measure the ratio of heads that appears. This table that we're doing, this is an experiment. So this is going to be the empirical probability, right? It's going to be the data that we're getting from a probability experiment. We know that the probability of heads, assuming it's a fair coin, should be 1/2. So let's see what happens here with these flips. So I already went through and I did this. So let's say we flip it. How many times did I flip it? I flipped it 10 times. So on the first flip, I got a tails. So the ratio of heads is going to be how many times we got a heads divided by the total number of flips. That's going to be 0 divided by 1, which is 0. So the proportion of heads is 0. On flip number 2, I did get a heads. So I got 1 heads out of 2 flips. So 1 out of 2. On the third flip, I got another heads. So I got 2 heads out of 3 total flips. The fourth flip, I got another heads. So I got 3 heads out of 4 flips. Fifth flip, I got a tails. So that's 3 heads out of 5 flips. Sixth flip, I got another tails. So that's going to be 3 heads out of 6. On the 7th flip, I got a heads. So that's 4 out of 7. I'll do a couple more here. 8th, I got tails. So that's 4 out of 8. 9th, I got tails, which is 4 out of 9. And 10th, I got heads, which was 5 out of 10. So we could kept on going if we wanted to. I stopped at 10 because it gets the point across. So let me take this data and plop it down on this graph. So the vertical axis is going to represent the proportion. It's going to be the proportion of heads. So it's a proportion. So it has to be between, it's a ratio. Has to be between 0 and 1. And the horizontal axis here is going to be the flip number. So it's going to be how many times we flipped it. Which I flipped it 10 times. Okay, so I have the graph filled out. I just filled in the remaining numbers real quick. So let's kind of plot this data here. So flip number 1, we had a proportion of 0. So I'm going to put a dot right here, 1 and 0. For flip number 2, we had 1/2. For flip number 3, it was 2/3. So that's going to be about right up here. Not going to be perfectly accurate. Flip number 4 was 3/4, so that's going to be right here. Flip 5 was 3/5. So that'll be about right here. Flip 6 was 3 out of 6. 3 out of 6 is 1/2. Flip 7 was 4 out of 7. Flip 8 was 4 out of 8, which once again is 1/2. Flip 9, 4 out of 9. A little bit less than 1/2. And lastly, flip 10, 5 out of 10, which was 1/2. Okay, so what this says, what this is showing here is actually the law of large numbers at work. So it's saying that the more and more that we do this experiment, this proportion of heads should approach the classical probability of getting a heads on one flip, which is 1/2. So here's 1/2. So there's 1/2. So it's saying the further along to the right, eventually all of these dots should kind of get closer and closer to that red line of 1/2, which is true. That's exactly what they're doing. It's getting closer to the 1/2. So that's actually the law of large numbers here. All right, so for the next thing here, so that was law of large numbers. For the next thing, we have the range of probabilities. So the range of probabilities, what this means is what numbers can the probability fall between. So the probability of an event E always has to be between 0 and 1, including 0 and 1. So that just means probabilities are just always between 0 and 1. As a percentage, it would be between 0% and 100%. So if you're doing these questions and you don't get something between 0 and 1, you did something incorrect. So let's explain what these following probabilities mean. So let's say we have the probability of event E equals 0. So what that's going to mean is that we have a 0% chance of the event occurring. So that event, whatever it is, cannot occur. Okay, so pretty simple. Probability of E equals 0.5, so that means there is a 50% chance of the event occurring. And lastly, for the probability of event E equaling 1, that means there's a 100% chance of the event occurring. So that means the event has to occur or will occur. Okay, so hopefully that's pretty obvious, but just always keep in mind that your probabilities always have to be between 0 and 1. Okay, and then for the last page here, we have another kind of definition and mini formula coming up. It's the idea of complementary events. So we know that the sum of the probabilities of all outcomes in a sample space has to be 1. So that's a pretty important concept, which we'll kind of be coming back to at some point also. So the sum of all of the probabilities happening has to equal 1, because that's saying 100%. When you run the experiment, there's a 100% chance that something happens, essentially. So the complement of event E is going to be the set of all outcomes in the sample space that are not in event E. So it's everything but event E. So the complement are the set of all outcomes not in event E. So we're going to denote this with a little apostrophe, which you can call E prime. The complement of E is E prime. So based on what I wrote up here about the sum of the probabilities having to equal 1, that means the probability of event E happening plus the probability of the complement, meaning the probability that event E did not happen, has to equal 1, right? So either event E happens or it doesn't happen. So the probability of it happening plus the probability of it not happening has to equal 1. So we could rearrange this a little bit, which sometimes is going to be helpful. If you're familiar with algebra, rearranging equations, what we could do is we could subtract the probability of E complement on both sides. We'd end up getting the probability of E equals 1 minus the probability of E complement. Or we could start from that first one and subtract the probability of E on both sides. We would get the probability of E complement equals 1 minus the probability of event E. So these all mean they're all the same exact formula, they're just rearranged a little bit, but sometimes it'll be a little bit easier using one compared to the other one. So let's do two little examples here, and I think it's the last page. Okay, so first example, if the probability of event E occurring is 0.3, what's the probability that the event does not occur? So hopefully it's not too difficult here. So we have the probability of event E is 0.3. So we're looking for the probability of E complement, right? So the probability of E complement, based on what I have written right above here, is going to equal 1 minus the probability that event E does occur, which is 1 minus 0.3 because we're given it in the problem. So it's 0.7. 1 minus 0.3 is 0.7. So we get the probability of E complement is 0.7, which, looking back at it, hopefully that's pretty obvious. That's saying there's a 30% chance that event E happens, so there has to be a 70% chance that it doesn't happen. Okay, let's make it a little bit harder here for the last one. Suppose 24 of 30 students pass the statistics exam. What's the probability of randomly selecting a student who did not pass the exam? So what I'm going to do here, I'm going to label. I'm going to say let's let event E be the event that the student passed the exam. So it is good to label your events like this. So if that's the event E, then event E is going to be the event that the student did not pass the exam. So we're looking for the probability that the student did not pass. So that means we're going to set it up the same way that we just set it up. Probability of E complement is going to equal 1 minus the probability of E. 1 minus, so the probability of E, 24 out of 30 passed. That means the probability is going to be, that's the empirical probability. It's just a fraction, 24 out of 30. Okay, so hopefully maybe we remember how to add and subtract fractions. When we're adding or subtracting fractions, we need a common denominator. So you could plug it in your calculator, but just remembering how to add and subtract fractions, you need a common denominator, which would be 30. So we would have to multiply 1 over 1 by 30 over 30, which would just be 30 over 30. And then we subtract the numerators. 30 minus 24 is 6 over 30. And that's going to simplify to 1/5. As a decimal, that's going to be 0.2. As a percent, 20%. So given that 24 out of 30 students passed the exam, that means 6 out of 30 failed, which once again should kind of be obvious. Maybe we didn't have to set up this little equation for it. So 6 out of 30 represents 0.2, or 20% of the students did not pass the exam. Okay, so that is it for section 3.1.